Okay. So let's talk about, you know, kind of what's our operational definition of a system. Okay. And you have something, right, that you put an input into, and it causes an output. And so far, the things that you're used to are inputs of time that are functions of time, and outputs that are functions of time, right? So physical systems, right? You have your oven at home, and you put an input into your oven to turn on to 450 degrees Fahrenheit is the starting temperature when you're baking an apple pie, right? Or if you're turning on the heat in your house, you go over and swing the dial or use your app um, to to tell the system to in fact turn on, right? Now, in this class, yeah, we'll be describing everything mathematically, but the most common systems, right, that you're going to deal with as an electrical engineer will be in the physical world, right? And will be circuits. And those circuits will be some kind of RC, or like in EE 112, right? You might not know it yet, but the circuits that would actually implement the functions you talk about are DSP trips or microcontrollers or anything like that. Where 118 tells you how to actually make the fundamental building blocks of that, right? Where EE98 showed you a resistor and a capacitor, and now we're going to have a system. So I guess that's the difference. In 118, they're showing you the circuits along with the digital systems. Here we learned the components and some physical relationships before you took your systems course. All right. Any questions so far? And I'll look in the chat. Okay. So now we do have some special names for things, right? Is that if, and we're going to call it H, right? If we put in an impulse into our system, right, we're going to get the impulse response. All right. And an example of this is, what if this system is what if the system is the 49ers stadium in Santa Clara, right? And what we're really interested in is sound, right? And we want to come up with, we want to kind of measure the sound system of the stadium, right? So you would put in an impulse response. And then whatever sound waves you measured out would be the impulse response. Now, what is that impulse response? It's a delta function, right? Which is something.
Professor,
Yep.
are you saying that we input impulse response or the output is impulse response?
The impulse input.
Yeah, okay.
Oh, yeah, you're right. As time goes on, we start to use different terminologies for things. But yeah, H impulse is in fact the impulse response, and that would be the output. All right, thanks. Any other questions? Good question. Thank you.
Hello. So the step response is the integral of impulse function?
Yeah, exactly. We're going to review that in just a bit, though. Okay. So the question is, how do we get a delta function, right? Which is something that's infinitely high and kind of infinitely thin, if you will, right? And what you can do is all you have to do is make a loud, brief noise, right? Because it takes time for the sound waves to propagate throughout the stadium. And as long as the length of your noise is shorter than, much, much less than the time it takes to propagate back and forth through the stadium, it'll be okay. And so what some people do is you just pop a balloon. You just hear a pop and then you record it. Now, yeah, it's got to be loud enough so that you can still detect the response. Okay. Now, the step response, right, is you just put in a step function and you get out a step. And yeah, the this is the equation. Oops. All right, which is just like the step function is the integral of the delta function. If I've measured the impulse response and I want to know the step response, all I have to do is integrate. All right. And what if we had a ramp? Well, that would be the H ramp. That's just what you would call it. And another useful thing is if you integrate that. And yeah, if you know the ramp response, take the derivative and you can get the step. If you know the step and you need to get the impulse, you can take the derivative of it, right? And, you've all tested circuits, right? Your function generator, right? You have a square wave, you have triangle waves, things like that. Oop, that's not a square wave. That's a sine. Right. Well, there's really no such thing as the impulse response. And so many times what you're doing is you're taking the step by using a rectangle, and you're making sure that this is long enough for any for the signal to get to where it's going, right? But physically, something that goes from 0 to 1 at, and never comes back down, right? That isn't really in zero time, right? That's not really physical, right? Same with ramps. In engineering, everything's an approximation. Any questions so far? So this is a course on systems, but there's two important things. Okay. In electrical engineering, right, we almost always are assuming that the system is linear. And we're also assuming that the system is time invariant. And, it's linear time invariant, right? LTI. And we will assume this so much in 110 that we will forget that we're even talking about these kinds of systems. And sometimes you might think that nonlinear time variant systems don't exist, right? So the thing about linear systems, right, is that if if I have an input of t, I have a function output of t. All right. And if it's linear, if I scale this, right, then all I have to do is scale the output and it's the same thing, right? So for example, here's a system. Right? Where effectively F out equals F in. And I'm leaving off the time because it just takes too long to draw, right? So if I put in out, if I put in 1 volt in, I get 1 volt out. If I scale it by 2, I get 2. If I scale that by 2, I get a half. All right. Now, something that you have to consider though is the power supplies, right? An op amp can't go beyond its power supply, right? So if I scale this input by 10, right, my output's going to be 5. And that's for only certain kinds of op amps will do that, like the LT 1630. if you're used to the LM741, if the power supply is plus or minus 15, you can really only get about plus or minus 12 out of it. All right. But so the thing is this circuit or this mathematical relationship is linear, right? But this physical circuit is linear up to a point. Okay. And, you know, just like, you know, what if we had a non-inverting gain stage, right? 1K, 9K. Out equals 10 in. Well, if my power supplies are plus 5 volts and minus 5 volts, and I put in a 1 volt, mathematically I should get 10, but I'm only going to get 5. If I put it in minus 1, I should get minus 10, but I'm only going to get minus 5, right? So there's a range where everything actually works. And these ranges, these limitations are all in the data sheet. And many times in your circuits class, all these things have been taken into consideration in the lab manual so that you never actually kind of make a mistake. All right.
I have a question.
Yes.
What do you mean by negative voltage? What does it do?
I don't have my headphones on today. Can you speak up?
I'm saying like the output is minus 5 volt. Why is the voltage is minus negative voltage? That's what I'm saying. Hello?
Yep, I hear you. I hear you. You mean, why do I say I put these numbers here?
I'm just saying like when we have like minus 1 volt in and then we got minus 5 volt out. So what the minus voltage actually do?
So what is this right here?
Yeah.
Right. Those are the power supplies. It's like the batteries that power this, right?
Oh, okay.
So the thing is, right, remember we had this equation A vol V plus minus V minus, right? And that was out, and that was what's inside the op amp. In order to get this behavioral supply, this behavioral function, right? There's all these transistors that are connected to do that. And those transistors need to be powered. Otherwise, it won't work. All right. So in order to get a bigger voltage out than you put in, that energy has to come from somewhere. And you need positive and negative voltages to do that. Okay.
Okay, thank you.
Yeah. Okay. Yeah. And you can always see me later. So, so if I put in minus 1 and I multiply it by 10, I should get minus 10, but I'm not supplying that enough voltage. So I only go to minus 5. All right. So now what does time invariant mean? Right. So if let's say I put in a step and it goes into a system and I get that function, right? Well, it doesn't matter if I put that step in at 0 or even like 10, right? The only thing that happens is where it starts rising is just shifted. All right. So it doesn't matter if I put in 1 volt today or tomorrow or the day before, I will get 1 volt out of that system. right? It doesn't matter if I put in 0.1 volt yesterday, today, or tomorrow, I should get 10 times 0.1 or 1 volt out, right? Meaning it doesn't change in time, all right? But in the real world, actually, things do change in time. Maybe you don't realize it, but resistors get old, right? And when they get old, their resistance changes. And if their resistance changes enough, right, your gain won't be the same, right? What if the resistance of the 9K goes up to 10, right? You're going to get a different gain. Now, so even selecting a resistor, right, for something that's going to go into space and have to be, good for 10 years, right? Well, we put in a step response today and we put it in 10 years from now, right? Is it time variant in 10 years? And so practically, time invariant for us really kind of means, hey, there's a time for which we'll guarantee this circuit to work, and past that, you're on your own, kind of thing. All right. And but mathematically, and the things we're going to do will always be time invariant, right? Now, let's talk about humans. Right? We are not time invariant, right? We get used to things, right? So let's take the movie Pirates of the Caribbean 2, and spoiler alert, I'm going to spoil the ending for you, is that Captain Barbossa shows up at the end of the movie to lead the pirates on the mission for the third movie, but you think this guy has died in the first movie, right? And that's a big reveal, and it's a surprise if you've been following the movies. So you see this exciting thing happen in a movie, and you're like, oh my God, that blew my mind. I thought he was dead, but no, he's alive, right? But then you watch it the second time, and it's not as exciting, right? You watch it the third time, and then after a while, you know it's coming, and it's just not as exciting, right? We accommodate to it, okay? And then as far as being linear, right? We as humans have a phrase, the straw that broke the camel's back, right? Where you can keep adding something, increasing an input until finally somebody explodes on you, right? If you're teasing your brother a little bit and then a little bit more, you get nothing, a little bit more, you get nothing, and then they explode, right? So humans are not linear and they're not time invariant. And you have to be careful when people start thinking of humans as linear time invariant systems. All right. Any questions so far?
No questions so far, none. Yes.
Okay. No, that's all right. There's just one more thing I wanted to talk about, and I forgot to mention, is that we're only talking about one input, right? But if I have 1, 2, 3 inputs, and I have H1, 2, 3, that's the same as 1 H1, 2 H2, 3, H3. And then summing them all up. Okay. And right, if we were to write a right, VN equals VR plus VL plus VC. Right. And so these are, you can usually just tell when you see add or subtract, right? Because that's just a linear combination. All right. But the thing that you probably oops. This is in one. It's that superposition, right? So if I do V out for in one only, right? That means, oops, I short this input, right? So they're in parallel, fine, but no current can come out. And so that means there can be no voltage drop across these resistors. And so effectively, this input is tied to ground. And then you would just look by inspection that the output is minus RF R1 VN1, right? And then, and I'll just try to quickly draw it again. I can find the output to VN2, right? Well, I short one input, right? And then notice that's R1, that's RF, that's a voltage division. So we get RF, R1 plus RF plus 1 plus RF over R1 VN2. Now you could have used nodal analysis and solved for this all at once, right? But superposition only works if the system is linear. A quick example of what is not linear is this diode. All right. And you might think like the inverting summer, I can just figure out each one of these and sum them together. No. That diode equation is e to the minus VD, and there's a function in there. So no, you can't do it there. All right. But those are systems that you've seen superposition before, you know, for a day or two. Well, that's what it's like. Any questions on that? Okay. In a static system, right, f of t equals cosine of t. So whatever t changes, f of t changes instantaneously, right? Where in a high pass circuit step response, this takes time. There's an exponential delay in there, decay in there. And that means it's dynamic. Okay. So static things can't have derivatives and they can't have integrals, right? Which really, another way of thinking of it is they can't have memory, okay? Because to calculate the derivative of something, right, I need the change in time and the change in height, right? So that's memory. If I'm calculating the integral, right, I'm finding the area under the curve as we go in time, right, which has the dt, okay? Dynamic, you need at least one dt, either a derivative or an integral, right? And the components are really capacitors and inductors because they have integrals and derivatives in there, right? These are energy storage elements, right? Capacitors, right? They take time to fill up with voltage before they can start with, so that they, to fill up with charge so that they can, you know, you can measure a voltage across them, right? If you think about it, or if I have a tank and I'm just filling it up with water, right? The wider the tank is, the effectively, like, the bigger the capacitor is, the more water, the more charge, right? Inductance is a little, it's storing its energy in current flow, all right? But they are memory elements, really, all right? And if anybody has heard of dynamic RAM, that's effectively a transistor turned into a capacitor, and you store your high or your low voltage on it, and it dissipates over time, so you have to refresh it high or refresh it low. But you know, that's, capacitance is one way to store energy. Okay. Now, the impulse response, or I kind of just did the op amp review for the homework, but the impulse response is really part of the 98 review page, which some of you, I think, might already be on. Okay. But it should take you right to circuit analysis transients. All right, if you have trouble going through that link, it would be in these review notes. Okay. So this circuit right here, right, part of it will be on midterm 1 and midterm 2. The only difference is it'll be going into an op amp. All right. Now we're going to review how to come up with the transient response of these circuits. But just so you know that in 110, we're going to learn a simpler method. The reason why we're starting here in the time domain is that we're going to use convolution next time, which starts in the time domain and has integration. So it's a good review. All right. And you can just see everything there. All right. So the question before us is, what is V2 of time when Vn equals Ut? All right. And what I'm going to show you is how to do that pretty much with impedance of a capacitor J is square root of -1. Omega is frequency in radians per second, and C is capacitance. Right. And so kind of just using regular voltage division and is a circuit open and closed, we're going to come up with what's going on when T is much, much less than 0, when T equals to 0, and when T is much, much longer than 0. All right. Oops. This is just a simple step response. Nothing's really drawing to scale because much, much longer than or greater than depends on the system in question. All right. So we're just talking relative. What that means, we can define that later as tau. You probably might be remembering that. So let's think about it. Case 1, right? Vn equals 0. Vn is DC, right? I know maybe I've drawn it changing, but that's just a shaky hand, right? That's just DC. Well, ZC is 1 over J 0 C, which is infinity, right? So if this is infinity, That's an open circuit. No current can flow. If no current can flow, there's no voltage drop. And that means these two nodes are equal to each other, right? And so that means V2 equals V1 equals 0, right? What about when T equals 0? Right at that spot. Well, we have an infinite slope right here. That's like omega equaling infinity. That means ZC oops, that's infinity, equals 0, right? So now we have this. Now, sure, now current will flow, right? But there's a voltage drop here, but this node is still tied to 0, so V2 T equals 0 equals 0. Now here, we're back to DC again. Right? Omega equals 0. ZC is effectively infinity. And we're back to this picture. But Vin now is 1 volt. So even though I is still 0, there is no voltage drop, right? And so V2 equals V1 equals 1 volt. Okay. All right. So let's just well, before that switch, right? It's 0. After that switch, it's 1. But what is this shape here? Right? We know that before the step, it's going to be 0 because it's acting DC. The capacitor is open, no current flows. And so there's no voltage drop across that resistor. Then once we're back at DC again, same conditions, except when V2 equals V1, V1 equals 1 volt. All right. And we're just like, how do we get here? All right. And again, there are many ways to do how do we get here. Okay. The time domain can be a little more difficult when using differential equations. So what sometimes can be the better thing to do is find the natural response, which is V equals 0 VC is set to a value, see what happens. All right, so let's redraw this circuit. I'm going to draw it like this first, right? Because I've shorted it. But this and this are the same. So if I've charged up this circuit to 1 volt, 10 volts, right, the charge is going to flow out and dissipate through the resistor, right? So even though electrons are negatively charged, in circuit analysis, we always use the flow of positive charge. So that would be I1 coming out of the resistor. And then I would have I2, coming out of the capacitor. And I have I2 coming out of the, flowing through the resistor. All right. So I have something entering the node, I1, equals something coming out of the node. Oh, that's nodal analysis. All right. I2.
So Professor,
Oh, is there a question?
yeah, so it's not serious, like the connection.
I'm laughing because that's a tricky thing. And I've been burned on it when I was learning it myself, which is why I'm laughing. I'm not laughing at you. Is that the thing is yeah, you could say that this is a series circuit in terms of voltage and current, but in impedance, ideal voltage sources have 0 impedance. And so these are still in series, aren't they? Because I can start here and go around. But yeah, it's also kind of in parallel because you can go two ways. It's you probably hate me when I say that, but try not to think about that. Okay? Because it's right, going around one loop that way puts it in, in series, but you can go around the loop the other way. Well, then that means it's in parallel. Now, really, maybe that in fact is really the same path, right? It's just you're going one way or the other. But the thing is I'm not finding an equivalent resistance, right? I don't have an ohm meter here and I'm measuring the resistance of this circuit, right? Maybe that helps. This is just, I've charged this capacitor up and the current is going to flow this way. It's not really going to flow both ways. It's only going to go in one direction. All right. So maybe let's keep it series for now. But still, that's a very thought-provoking question. So let's see. I2, right? Ohm's law, V2 minus 0 divided by R1, which really just equals V2 R1. Now, I1, can we use Ohm's law? Not in the time domain. We'll find out that in the frequency domain, we sure can. But what is that current? That current is equal to capacitance dV2 dt. However, it's really minus. And the issue is, let's say I have a C. Let me not do that. Keep a dark color here. Here's the current flow, right? So I have to put plus minus in that direction, right? Because Ohm's law is V equals IR. When the current is going one way, I have to put the plus at the beginning of the arrow and the minus at the end, right? However, so what that means is, all right, I'm going to use red, right? If I had a voltmeter, right, the positive end of the voltmeter would be here. The negative end of the voltmeter would be here, right? And I'd be measuring it. But that is VC, the definition of VC1. But VC1 equals minus V2 in this case, right? I've labeled this V2. So that really means is I take my oscilloscope and I put that on node 2, right, the positive lead, and then I take the negative lead and put it on ground, and that's my scope. That's my symbol for a voltmeter, all right? And so if you don't put that minus sign in there, you will get a circuit that ultimately has exponential increase, which doesn't match reality, which would basically let you know that something had gone wrong. All right. So let's just rearrange this. dV2 dt equals minus, and I'm going to go back to R1C1. Oops. V2. Now these are functions of time, right? Now, I've read all the books about, when in differential equations, when they're solving for this, and they will come up with all these ways to solve it. But the truth of it is, the derivative of the thing, in this case, V2, a function of time, if that equals the negative of the thing, right? And that's just a scale factor. Then the only thing that can fit that is some kind of decaying exponential, right? Because if I take the derivative of this, I get minus alpha e to, right? If I take the derivative of that, right, what do I get? I get minus alpha e, right? There's the original thing, and now I've taken the derivative. And so sometimes I feel that the mathematical tips and tricks you learn in differential equations are a way to kind of solve or solve things. But sometimes you're really kind of guessing. Does a sine function work? Well, let me take the derivative. No. Does a square function work? Well, let me take the derivative. No. Does a tangent function work? No. So let me try exponential. Positive. No, that doesn't work. Oh, let me try negative exponential. Oh, wait, that's close. All right. Now, here's the thing. Right, we have some boundary conditions, right? T less than 0, 0. T equals 0, 0. T greater than 0, 1. All right. This is the part we're going to concern ourselves with. All right. So we have these boundary conditions, and we have this kind of function here. But the thing is right, that there could be, we could add a linear to this. We can scale it to fit this. So really, at this point, we know that we have to fit this, right? We got the fact that it's this from differential equations, that was the natural response, right? Where if you put a charge on that capacitor, it will decay over time, right? But we're doing the step response. So that's a different, it's the same system, but a different input, right? So now we can, so if it's 0 before time is less than 0, well, we can just take V2 and whatever we come up with in here, we can just multiply it by a step function, right? In circuits, they would just say, subject to t being greater than 0, right? They didn't use the step function notation. So when so t equals 0, right? When t equals 0, v equals 0 equals a plus b e to the 0 equals a plus b. Okay. When t is much, much greater than 0, right? Or we call it infinity. All right. So Vn is 1. I mean, V2 is 1, right? We still have a e to the, b e to the minus infinity, right? That goes to
A quick
0.
question. I have a quick question.
Yep.
What's the
Yeah.
boundary
please.
conditions? What's the word next to the condition on the top left?
Boundary t less than 0 conditions.
Oh, that's boundary.
Boundary, yeah. Sorry. Okay. So this is derived more fully in the notes, but you use these conditions and then you get V2 step equals 1 minus e to the minus t. Okay. All right. And now we're going to kind of fly. Okay.
So Professor,
Yes.
so is that like another step after the first one? Or
Let me redraw the equation. Okay. What's going on here is if t is less than 0, this gets infinitely big. It forces it to this kind of shape. Okay. So if for t less than 0, this starts to get really big, and you would get this, right? That step function multiplies it by 0 up to that point, and then you get this part of the equation. All right. And we've, I've kind of plotted these equations out prior lectures. All right. So I have some nice plots of them in the other notes. So now, So what's the ramp of that? Well, you just integrate, which equals t minus okay. Now remember, this all started at 0, right? And we had a step function in there that I forgot to write, but really this whole thing is multiplied by a step, which t times step is ramp t. Minus 1 times step is minus ut. And then I would have ut r1c1e to minus t. Okay. In a similar vein, v2 impulse is the derivative of the step okay. And now we're really going to fly. Now I just want to start you to get used to the terminology, but this is the low pass filter. And this is the high pass, right? Now, notice that in this circuit, this is linear. It doesn't matter the order, right? Vn equals Vr plus Vc, right? Here, it's Vn equals Vr1 plus Vc1. It doesn't matter the order, right? And the device voltages, Vr1 low pass equals Vr1 high pass, right? Vc1 low pass equals Vc1 high pass, right? And so here's the thing. That means V2 low pass equals V1 to 2, meaning measured across here, high pass. So I already know this. And you know the input. Well, then all I have to do is solve for algebraically for R1. Right? So what that means is if I say Vn equals V2 high pass plus I could just say V2 low pass, right? And that's just 1 minus e to the minus t r1c1, right? Well, and for t greater than 0, Vn is 1. I can just have 1 equals V2 high pass plus oops. Okay. Now I can integrate this to get the ramp, but there is a problem when you take the derivative to get the impulse. And I'd rather now go to the notes. All right, so to find the impulse response of the high pass, right, again, this is this relationship, right? And all I have to do is the ramp is equal to Vn minus the impulse response of the low pass. Well, Vn for an impulse is a delta function, right? And then I get this relationship here, right? So here's the inverse of the step function, impulse response. Oops. And then I just have this delta function, right? But if I were to just take the derivative of this, right, I get this. And again, this is all with step functions in it. Well, where'd that minus 1 come from, right? Or you might think that, here I have a minus 1, but here I have delta minus the impulse response of a low pass filter. And the problem is that when you integrate the impulse to the step, there's a boundary condition that you have to satisfy, which you kind of have to cancel out this minus 1, which is in fact really a minus ut. Well, how do you add a plus ut to the impulse response? Well, the only way to do that is to put in a delta function, right? Because when I integrate this in time, I get the step function. I get a positive step function, which then will cancel out this, and then I get what I want. All right. So that one's a bit of a kind of a pill, right? The ramp, you're using the same algebraic relationship as before, and you get t minus t, right? And then when you cancel it all out, again, it's all with multiplied by step functions. In this case, you get the same answer when you integrate. All right. But these shapes, right? Here's a low pass, right? And it takes 5 tau to get to where you're going. And this can be scaled up or down because it's linear, right? This is low. And for high, right, it takes 5 tau to discharge, right? and this is the step. All right. Now, interestingly enough, for the impulse, we get this. The impulse for the high, that's our delta function. This and this are just inverses of each other. All right. And so knowing the difference between these two shapes, having that as an input or having that as a circuit, or this is a circuit, and then having a gain stage here. I'm leaving out some of the details. Right? So we have a high and we have a low. And we're going to get into that more as time goes on. But I'm telling you, these shapes here versus time, you will see on the midterm one, and you will see on the final exam. Okay. There's more to it than just that. All right. But, all right. Any questions before you all head off to 112?
So Professor,
Yes.
so the position of the capacitor like determines whether it's low pass or high pass.
Yep. Yeah.
Why is that?
Because this is the output node we've been talking about, right? But VC is the same as this VC. VR is the same as this VR. So in fact, this circuit gives me a high and a low pass. If I put my I can, well, oscilloscopes in general, one input is tied to a common ground, but actually the ADLM kit is if I measure from here to here, and I can get one thing, I can get high pass. And if I measure from here to here, I get low pass. And so the thing about these filters is that, you know, usually if you have if low pass is there, you must have high. Okay, if you guys, I know folks are going, but so I know that just notice, right? We started off kind of slowly, but then we just kind of use, mesh analysis to show that these are equal to each other, right? We have op amps that can be linear, static, or whatever. We have these responses here. And again, we have a better, more efficient way, but we're going to do convolution next time, which is maybe a more formalized method than what I've been showing you to do this. But when you look at one of these circuits, when is it DC? Oh, it's open. You know, when is the frequency really high? Well, then that makes it short. And just by that and voltage division, or actually it wasn't even voltage division, it was the current is 0 or the current, you know, either it's a wire or it's open, or there's finite current and no voltage drop, or 0 current and no voltage drop, right? Anyway, have a good day. I'm gonna.
Professor, what did you circle in the box? It's a low pass and a high pass, or?
Oh, wait, this here is a low pass. Oh, sorry. This is low and that's step and that's impulse. This is high pass and that's step and that's impulse. And now this and this, right? Knowing those two shapes will be on the midterm, and knowing these too. But what I'm saying is this kind of shape, which one of these shapes goes to this? Which one of these goes to here? This is a slightly different question. This will be a different question that actually I'm going to show you next time. Okay.
Okay, all right, thank you.
Yeah, thanks for asking that.
Yeah, Professor, I just want to ask a question about homework number 2. I don't know, but to me, I only have 1 try for it.
Really?
Yeah.
Send me an email, okay? That's not right.
Actually, it's 100 tries. It's 1 try for the whole assignment, or 1 try for each question in the assignment, but you can try the assignment 100 times. I don't know if that made any sense.
I mean, it
So-
might, sometimes I have it give you different questions, but you should be able to do them as many times as you want and not get downgraded, okay? But just email me if you're having an issue. Just email me your name, your ID, and the exact question you're having an issue with. And it's even nice to get a screen grab, okay?
And
Once-
secondly, I'm
What can
sorry.
happen is they change the system on me, and then questions kind of stop working every once in a while.
Earlier on, you spoke about
Oh yeah,
office
so
hours.
yeah, you can. Here's the thing. Some people. So yeah, you can repeat the whole assignment, not just an individual question, because some people will kind of just keep entering in an answer until they get it right. So I have to kind of put in a cost. I don't want to put in point cost. So the cost is your time. And that's okay. My ears are bad. If your mic is bad, my ears are bad. Because I don't think you guys can read the chat in the video.
For me, when I do the home app homework, it cost me like 20 point 25 points for that if I redo it for the second time.
That okay. Send me an email. That shouldn't. It's supposed to be set up for that not to happen, right? But sometimes what they do is they update the system and things get changed. Okay. So just email me. All right.
Okay.
I have a meeting at 4:30. Okay. So I have to kind of go.
Okay, thank you.
Professor David,
Yes.
was there supposed to be a homework 2B?
Excuse me?
Was there supposed to be a homework 2B on the canvas?
Yeah, there's homework due.
No,
It was
homework
due-
2B. Like,
Oh,
was there
no, because I didn't like it anymore and I got rid of it, but I just couldn't be bothered renumbering everything. No,
Oh.
no 2B does not exist.
Okay.
Okay?
Okay, have a good day, Professor
All
David.
right. Good question. Take care. Bye.
Hey, Dr. Parent.
Yes?
I'm stumped on question 8 of homework 1D. I know that you have to go, but I was wondering if maybe you'd have time later today to go over that.
Can you kind of send me an email about where you're stuck?
Yeah, I can do that.
Yeah. Okay?
All right, thank you very much.
All right. Take care. Bye. All right. I'm really, really going this time, guys. Take care.